Good day, everyone. Welcome to Chemistry with Professor John. This is General Chemistry 2, Chem 202, and we'll be discussing equilibrium today. All right? Equilibrium is reactions or reaction that can go both way. Just to make it simple, the for reaction that's reversible, that's what I mean. For example, carbon dioxide react with water to become carbonic acid, and notice that the arrow go towards the products, but also um, there's one that goes back to the reactants. Remember, reactants are um, the one on the left side, products are the one on the right side. Okay, so reactant. Okay, now reversible reactions um, mean the reaction go towards the product and can also go back to the reactants. The when the rate of reaction that go forward towards the right, I'm gonna keep saying towards the right from now on. The right means product, the left means reactants. The rate towards the right, that's the rate forward, and the rate reverse towards the left. Those two rates are the same. That means when the rates are the same, that means there's no change in concentrations of reactant and product. So product and reactants are present at the same time. When the rate forward and backwards are the same, we call that equilibrium, and we can calculate at that moment there's unchanged concentration of product and reactants. So we plug in the equation and calculate the ratio, which is known as equilibrium constants. Okay, so this is an example what happened in our blood. And cell bring the CO2, and CO2 get in the blood vessel, and we release them by exhaling, and then we inhale oxygens, and oxygen get in the cell. Okay, now back to the chemistry part. Let's say we have a reactions that M capital A, that's reactant A. M is the balance coefficients, plus NB give us XC and YD. Okay, the products are C and D. So those are you see coefficients. And then those are reactants and products. So we're going to focus on either gases or aqueous. Species mean molecules or compound. Okay, so when we get so let's say we got such and such amount of products and such amount of reactant at any time, and we get the ratio. Okay, the ratio is known as the quotient, and it's called QC. The sub C means concentrations. Okay, so that will be product. It's always gonna be product over reactant. Okay, always product over reactant, and they multiply together. And that's all that's explained right here. Concentration must be molarity. Product concentrations, products are in the numerators on the top. reactants and denominator on the bottom, and then you got all the coefficients. Those are the power, raised to the power. So that's the equation for QC. Now, if QC at equilibrium, like I mentioned earlier, that's when there's no more change in the concentrations. When the rate towards the product and the rate towards the reactants are the same, it's like the reaction going back and forth. And when those two rates are the same, there's no change in concentration of C, D, A, and B. You start out with AB, and you start out with A plus B, C plus D. You start out with AB at the beginning. It's a lot of A, it's a lot of B, but as the reaction progresses, C and D will be formed, and then we'll have less A and less B. But at equilibrium, so sometimes it forms too much C and D, and then they go back to reform A and B. So back and forth. But at equilibrium, everything will be stable, the concentrations. So we take C and D time together, and to the power C and D divided by A and B to the power of the coefficients, and we got ourselves Kc, which is equilibrium constants. So Qc is at any time, but Kc has to be at equilibrium. Okay. All right. So I'm going to write right here at any time at equilibrium. Okay. Next. All right, and don't be confused, K with the rate of reactions. Now the value of equilibrium constants is independent of the starting amount, okay, of the substance that we dealing with. And it does depends on the temperature, okay, and of course how big the value of K is, it tells us about the reactions. Remember K is products, or Q, product over reactants. So over reactant. So the larger K, the more the product. That's the message. All right. And the units are all over the place, so we decide not to have the unit for that, for K and Q. Okay, now if K is very small, okay, because remember K is product over reactants. If it's that ratio is very small, we don't have much product, so it's mostly reactants. The denominator, which is the reactants. If K is really small, I mean we have a big denominator, which a lot of reactants. On the other hand, if K is very large, then we have a lot of products. Okay, and of course the value K has now no telling about the reaction is fast or slow. That's little k, okay, that's rate constants. Okay, for Kc and Kp, remember P is pressure, and C is a concentration. Okay, And delta N is the change in number of moles of the gas, a product divided by reactants. So we'll do the practice on that one. Okay, and I'll show you guys how to do delta N. It's the total number of moles of product minus reactants. R is a universal gas constant, and temperature obviously in Kelvin. Okay. Okay. Now, Legendre principles is really awesome. It's help us to predict which way the reactions goes. So you got reactant and you got product. Okay, reactants on the left, products on the right. Now, okay. Now, if we add more reactants, so basically the principle said, if whatever we do, it's gonna go the other way. So to make it simple, so we add more reactants, it's gonna shift to the right. The reactions, of course, because reactant will react together and make more products. So the equilibrium will move to the right, making more products. However, if you got cold feet, you make so much product, you want to go back to reactants, then if you have extra product, the same kind in hand, or one of the product, doesn't matter, you add to the reaction mixture, then you will get more reactants because it will shift the opposite way. Okay, so that's basically what it said. When a chemical system or reaction is at equilibrium already, and we disturb it by adding reactants or product or increase the temperature, it will shift to the direction that counteract with that additions or disturbance. Okay. The okay, so here basically the summary, and it's gonna change. So all the concentration will change, and it's gonna change the concentration product and reactants, and then to reestablish the equilibrium. Now, as I mentioned, adding reactants or product, it will go in directions that consume part of it. So these are the idea. Now, if we add pure solid or liquid, it will not change the reaction at all. Okay, because those are not part of the reaction solutions. Okay. If you increase the temperature, however, you increase the heat of reactions, and it will affect, okay, the reactions. Now, how does it do that, right? So if the forward reaction is exothermic, so that's gonna hot, and if we increase the temperature, exothermic is already hot. If we increase the temperature, that's not favorable. Therefore, K will decrease. Okay, so we'll get less product. So if an exothermic reaction, we don't want to increase the temperature. Okay, because heat is a product. If we increase the temperature, we add more heat, so the reaction will shift to the left, and therefore K will be decreased. If the forward reactions, forward mean making product, is endothermic, meaning heat is needed, then obviously it makes sense. If we increase the temperature, you add more heat, and then it's gonna go towards the right. So K will be higher. Okay. Catalysts. Notice catalysts do not affect the equilibrium. They help to increase the rate only, catalysts, but not equilibrium. So the equilibrium will be reached a lot faster with the catalyst. And this is about the rate. And it show this one is show the with the catalyst. It's the blue one, and the red one without a catalyst. So the catalyst lower the energy barrier, and so the reaction will go faster. Okay, calculation, that's the final part. And when you set up calculations, here's go straight to the table. So let's say we have this example. Iodide react with iodide minus, reversible reaction, and forming I3 minus. Okay, so let's say we start out, it's always going to be the same. You start out with initial concentration. Okay, so let's say it's given is 1.0 10 to minus 3 molarity, and then change mean as soon as you add them together, something's going to happen. So let's say X amount of iodide react with X amount of I minus, and on the left side is always negative because reactant are consumed. On the right side, the product always positive because products are formed. So in the end, not the end, the equilibrium, in this case is the end, it's always going to be initial minus how much is used up, initial minus how much used up, to give us the equilibrium, the remaining, and that's how much products form. Okay, so when you do the K, it's gonna be X, which is the product, and there's no power because it's all coefficient here is a 1, 1, and 1, divided by 1.000 minus a time 10 to the minus 3 minus X, another one, so the same because they're the same, so it's going to be square. So if someone give us K or Kc in this case, we can solve for X. So let's say if someone give us well, whatever, I'm just going to make it up, 1.5 10 to the minus 5, for example. That's K. Okay, in this case it's Kc, and like I said, and solve for X. Okay, and actually there's an easy way to do that. So it could be something that small. Like I said, we can just make up numbers. It's or we can look up the Kc value for this reaction, particular reactions, and do the calculations. So this is going to be the same setup for whatever reaction you use. Like this, PCl5 decompose into PCl3 plus chlorine. It's always the same setup. In this case, you have reactant on the left, you got products on the right. Okay, remember product always positive, reactant always negative. And here's another one. You got one reactant, you got two products. Okay, and you would set up K or Kc will be X times X on the left divided by product on there. Okay, that's your k. And if we get the k value, then we can solve for x. Okay, so we'll do that. We'll look at the homework and in the books, and we'll go over some of those. All right, thank you guys, and we'll see you in the next video.